Exactly right. So we can tell that the tangent function could have asymptotes kind of like this rational function right here does, just because just like you mentioned, that cosine has values that would make it be 0. We know, for example, if x is 1, the cosine value is 0, so we can't have that. No, sorry, I mean if cosine is, or if x is pi over 2, then cosine of x is 0, and we can't have that. So we have an asymptote wherever cosine of x is 0. So x could not be pi over 2, or 3 pi over 2, or any multiples of pi over 2 or 3 pi over 2. So we have asymptotes at pi over 2. And then pi is okay. 3 pi over 2 has an asymptote. And then we have 4 pi over 2, which is also known as 2 pi. And then 5 pi over 2. So you might see a pattern beginning to form. We have pi over 2, 3 pi over 2, 5 pi over 2. So next would be 7 pi over 2. And we have a similar thing going on in the negative side of our graph. It's interesting to note that tangent is an odd function. And what that means is it's not symmetrical about the y-axis. We know cosine is even. If we draw the cosine function, I know this isn't remotely the way it's supposed to look, but it's symmetric about the y-axis, and that's how we know that it's an even function. Sine is not even, and neither is tangent. So tangent has a point at the origin. We know that because if we plug in 0, we get sine of 0 over cosine of 0, and that gets us 0. So we have a point at 0, 0. And we have equally spaced asymptotes on either side. So negative pi over 2 is also an asymptote. And negative 3 pi over 2 is also an asymptote. So on and so forth. So we want to determine if tangent is decreasing as x increases or if tangent decreases. But I might want to start by drawing asymptotes. I might just use a green horizontal line for asymptotes. So let's draw a period of this function. Now, ordinarily, a period would be 2 pi, but because we have a limit of our domain, because we have asymptotes, our period's going to be cut short. The period of the tangent function is actually just going to be pi. And let's take a quick look at our unit circle to determine if tangent is going to be increasing or decreasing as x increases. So we note that our angle starts at the terminal position. We start right here when theta equals 0. We have 1 comma 0. X is the cosine, and then y is the sine. And that's the reason why cosine starts at 1 when sine starts at 0, because the x coordinate of our angle theta is 1. So let's ask ourselves what happens as our line travels through the unit circle. So initially, x decreases, right? What happens to y as we move from 0 to pi over 2? What happens to the y-coordinate of our point?
It goes back to 1.
Yep, it increases. Y starts at 0, and it increases steadily until we get to pi over 2. And then after that, it decreases. So it's an increasing function. The tangent function only increases, which means that our graph is going to look something like this. So that is one period of the tangent function. So this behavior is just going to repeat after every odd multiple of pi over 2. So pi over 2 to 3 pi over 2, it's going to have the same thing. 5 pi over 2 to 7 pi over 2 is going to have the same thing. So that's about it. That's what the tangent function looks like. It has a period of pi. You can see it has restrictions in its domain. The domain would be all x, but x could not be either pi over 2 or any odd multiple of pi over 2 either. So it couldn't be, well, actually, 2 pi over 2 is acceptable, but we couldn't have n pi over 2, where n is an odd number. If n is even, that's okay. If n is 2, for example, we have 2 pi over 2. And we know that's in the domain, but we couldn't have any odd multiple. So that is the domain. And then we can see that the range is going to be all real numbers. In each period, we start at negative infinity. We travel upward to positive infinity. So the range is all real numbers. And our vertical asymptotes are located at every point where we have a restriction in our domain. So our first domain restriction occurs if we're starting at 0. Our first domain restriction occurs at this point right here. And we can tell that this would be our first asymptote. So that's where we get the asymptotes from. They just come from restrictions in the domain. So now this is the parent function. Let's see if we can graph the tangent function with a slight modification. So let's make just a slight modification. Instead of y is the tangent of x, let's do y is the tangent of x over 2. How does that affect the way the graph looks?
It's gonna grow wider.
Mm-hmm. The 1/2 on the inside, we have x times 1/2. It means that we're going to fit half of the curve in the space a full curve would ordinarily hold. So do you want to try graphing it?
Yeah, I can.
Here, I'll erase this.
So since it's gonna grow wider, so then would it go here and here?
Mm-hmm.
Okay.
So those are the new asymptote locations. Looks good. So that would just repeat time after time after time in each of those periods. So what do you think the graph of cotangent might look like?
It would.
So they're reciprocals of each other, which means that they'll have the same asymptotes.
Would it flip on the y-axis?
Yep, exactly. It would reflect across the y. So it would look like this. And that's it. That is the cotangent function. And it has the same period, same domain, same range. But one thing you might notice is that applying a constant multiplier out front doesn't really do a whole lot to it. It doesn't really generate a visible change in the same way that sine and cosine do. So just as a quick side example, we know what sine looks like. We know that the amplitude of sine is 1. And if we were to double the amplitude to 2, it creates a visible change. Very clear that this changes the shape of the graph, but it's not the same for tangent. So if we were to stretch it out and stretch it out vertically a little bit, for instance, here I want to shrink part of this. So let's imagine what would happen if we were to make our line increase by a factor of 2. It still goes through the origin, and it doesn't really have a noticeable difference. It isn't exactly clear that there's an amplitude change, kind of like there is for sine and cosine. So that's just something to keep in mind. The changes are more subtle for that reason, for cosine, for cotangent and for tangent. And then we're not going to spend a whole lot of time on graphing, but I do at least want to review the reciprocals of cosine and sine. So we have a secant and cosecant. Do you remember what the graph of cosecant looks like?
Yeah.
All right. Can you graph that for us? I want to start by graphing sine again. 1 period. So can you show us what the graph of cosecant looks like? So it looks like what you drew would be a transformation of the sine function. Looks like we drew sine of negative x.
Oh, okay.
So the reciprocal of sine is cosecant, and it's going to look like this.
Oh yeah, now I remember.
And the same relationship holds for cosine and secant. They're going to look the same. So that's about it. All right, let's see. So like I said, we're not going to focus a whole lot on graphing. I feel like you have the general idea of graphing down, so we're going to move on to a new section. We're going to be talking about the inverse trig functions. So we're going to be on page 343. So we are going to be discussing the notation we want to use for an inverse function. So just a quick reminder from basic algebra, if we have something like this, to find the inverse function, we call that y inverse. We have to switch our variables first. So we have x and then 2, and then it's no longer going to be an x there. I like to put y inverse because that's the quantity we're trying to solve for. And then from there, we just solve for y inverse. So we want to start by multiplying by 3. And then we add 5 to both sides, and then we divide by 2. So that's just the basics of how we find an inverse function. Just a quick refresher. So this y inverse is a really common notation, but the trig functions, they have their own unique notation for inverses. So at first, when I was first taking the class, I noticed how it was kind of confusing having a reciprocal, because sometimes they have a setup like this where the reciprocal of sine is cosecant. So that's why this notation isn't really used a whole lot in trigonometry, because mainly when we see this, we think of cosecant if we have sine, or we think of secant if we have cosine. So that's why this notation isn't really used that often with trig functions. So the notation we use instead would be the function with the prefix of arc, arc. So if y is sine of x, the inverse of y is going to be arc sine. And as you know, with inverse functions, the domain and the range switch. So we know if we're looking at the sine function, we have a period of 0 to 2 pi. Our domain is all real numbers, but our range only goes from -1 to +1. So the arc sine function, it's going to swap those so that the domain is going to be -1 to 1, and then the range is going to be all real numbers. Or is it? There's kind of an issue we have with that. There's a problem when it comes to the range being all real numbers. So whenever we take the inverse of a function and we want to graph them together, we want to imagine rotating the function 90 degrees counterclockwise. No, 90 degrees clockwise. So for example, if we have the function y is x squared, and we know the inverse function of that would be square root of x. So x squared looks like this, and then square root of x looks like this. And really, there should ordinarily be something there, but as we know, it fails the vertical line test, and it's therefore not a function. So that's why we don't have something on the bottom of the square root function. So as you can see, if we take this top function and we rotate it 90 degrees clockwise, we get the inverse. Ordinarily, this is how they all work. The sine function should be no exception. Let's see what happens when we apply the same thing to the sine of x function. So we know what sine looks like. It has a period of 2 pi and it goes on forever. It has a domain of all real numbers. So let's see what it would look like if we were to rotate it on its side. So we would go from -1 to negative pi over 2. And then it goes through the intercept because our original function does. And then it goes up to 1 and positive pi over 2. And it stops right there. We can't have a full period because it fails the vertical line test. Notice how we don't even have a full period. The sine function has a period of 2 pi, but the arcsine, very, very limited. Limited to this region. So the period of arcsine, well, I don't even really want to call it a period because it doesn't repeat. So the range of arcsine, actually, we'll call that negative pi over 2 to positive pi over 2. And the domain is going to be the range of the sine function, which is -1 to 1. So that's all it is. If you're going from sine to arcsine, the domain and the range switch. And that's why the arcsine function is so limited. And the relationship between cosine and arc cosine is going to be nearly identical. We know the graphs look very, very similar. So the same thing applies. And we're still going to have that same restriction that we can't have more than this region in the arc cosine graph either. So that's why the graphs don't have the same continuity that sine and cosine have. So let's talk about how to solve inverse trig equations. And I don't know if you're planning on taking physics at any point, but this is something that comes up a lot in Newtonian mechanics and statics and dynamics. Anything that deals with waves. So for instance, I'm on the next page, I'm on 344. Example number 1. We're trying to find the arcsine of -1/2. So when I see a problem like this, I like to maybe put it into its alternate form, which means that I'd write it as the sine of y equals -1/2. Well, maybe instead of y, I would use just an angle identifier. I'd probably just call that theta. Yeah, I like theta a lot better than y. Because we know that the sine function takes an angle, gives us an answer. And because the domain and the range switch when we go from sine to arcsine, it means the arcsine takes an answer and it gives us the angle needed to produce that answer. So we need to ask ourselves, well, what angle do we take the sine of and get -1/2 as an answer? And it's best answered with a graph. -1/2 would be this right here. And we have the same thing occurring on the other side as well. So we have this angle and this angle, and we know that they both generate a sine value of -1/2. So this would be 5 pi, no, this would be 7 pi over 6. And this one would be 11 pi over 6. So if we're talking about one full iteration of the unit circle, we have two answers. But sometimes in problems like this, they only have you give the first answer. They would give you some kind of limit like this. They would say maybe 0 is less than theta, less than or equal to, I don't know, maybe 3 pi over 2, something like that. But without a limit, these two are both valid solutions. We know that if we take the sine of 7 pi over 6, we get negative 1/2. And if we take the sine of 11 pi over 6, we also get 1/2. We also get negative 1/2, excuse me. So that's how we do it. We just want to ask ourselves what angle we take the sine of and get this as an answer. All right, let's talk about the next one. Is it all right if I erase this?
Mm-hmm.
So this next one, they use the notation that I'm not thrilled about, but it's doable. We have sine inverse of square root of 3 over 2. So we're trying to find an angle that gives us this sine measure. So this tells us that the sine of theta is square root of 3 over 2. Switch the domain and the range. So our problem solving process is identical to what we did in the last problem. We have our unit circle. We want to ask ourselves what angle has a sine value of negative square root of 3 over 2. So for this one, I'm only going to discuss one of those solutions. So we have a base of 1. We have a height of square root of 3, and we have a hypotenuse of 2. And this is one of those special right triangles. This is a 30, 60, 90 triangle. We can clearly see that the smaller angle is at the top. That's 30 degrees or pi over 6. And we have a right angle, which means that our angle theta has to be 60 degrees or pi over 3. So in this case, our angle is pi over 3. That's the answer to this problem. So I want to see if you could try the next one for us. We have sine inverse of 2. How do we want to start this one off? So we want to find out the angle that gives us a sine value of 2. So can you think of anywhere on the unit circle where just 2 appears? Not square root of 2, but just 2. Any of our special right triangles have a 2 anywhere?
Yeah, the hypotenuse of.
Exactly. The hypotenuse is 2.
Yeah.
So that would be a 30, 60, 90 triangle.
Okay. Maybe like this.
So we have 2 and we have square root. Oops, sorry. Here, I'll let you write it.
Like that.
Yeah, that is theta. So the sine of theta would be square root of 3 over 2. So not just 2. So this one is a little bit different. So this one, I feel like we're going to get a really irregular value just because this one doesn't have a set definition of these values like just the ordinary sine function has. So this one we may actually just want to use a calculator. For this, in this one, we want to just maybe put this into degrees first. I'd probably punch this into the calculator, make sure we're in degree mode, and after that, we will get an angle, which then we can convert to radians if we desire. But make sure you're in degree mode initially.
Wait, so do we have to convert the 2 to degrees?
Well, I would convert the 2 to degrees.
Okay. Is this the wrong equation?
This one looks right. We have 360 over pi, and pi is approximately 3.
Okay.
But let's graph the sine function real quick. I mean, this is all good, but I want to show you what happens if we actually tried to graph this function. So we know what sine looks like. Same amplitude, same period, same wavelength. So is there any angle that gets us a sine value of 2?
No.
No, you're right. There is not. So we could get the same answer just by continuing with what we were doing before, but we're kind of short on time, so I thought it might be best just to use this method instead. So we know that this one actually doesn't have a solution. So this is just no solution exists for this one, just because there's no an angle that gets us a sine of 2. So this one is no solution. So let's try to do the same thing with arc cosine. Let's see if we can find the arc cosine of square root of 2 over 2. So we're asking ourselves, what angle do we take the cosine of and get square root of 2 as a result? And, to me, it looks like this might have come from rationalizing. It looks like we may have had 1 over square root of 2 before, but they just rationalized it to get square root of 2 over 2. So we might want to think of it like this instead of like square root of 2 over 2. We might just want to think to ourselves, well, what angle do we take the cosine of and get 1 over square root of 2? And it is positive, and our all students take calculus trick for memorization tells us that our angle has to be either in the first quadrant or the second, because actually it has to be the first or the fourth. The cosine is going to be positive in both of those quadrants. So I'm probably just going to stick with the fourth here. We have a hypotenuse of square root of 2, and we have an adjacent side length of 1. So the only angle that has those characteristics would be pi over 4. So our angle in this situation is pi over 4.
Wait, can you explain it one more time?
Sure. So let me erase some of this. So we have it set up like this. We know that we take the cosine of some angle and we get this answer, but the question is what angle? And this doesn't really appear in the unit circle, at least not in that form. But I just recognized right away, doesn't this look like something we get when we rationalize something? This right here is the result of rationalization. So I think they actually started with, I think the book started with this. They had 1 over square root of 2. And what they did is they just rationalized this, and they got square root of 2 over 2. So we could actually write this as arc cosine of square root of just 1 over square root of 2. And this is a little bit easier to conceptualize because we know exactly where in the unit circle this occurs. So we can tell just from looking at this, we have 1 over square root of 2, that our reference triangle is going to have a hypotenuse of square root of 2 and an aside adjacent to our angle of 1. So now that I've drawn the reference triangle that has 1 as the adjacent side and square root of 2 as the hypotenuse, we just need to decide what angle this is. What do you think this might be?
45 degrees.
Yep, it's a 45, 45, 90 triangle. But in radians, this would be pi over 4. So that's our answer. The arc cosine of square root of 2 over 2 is pi over 4.
Okay, that makes sense now.
Excellent. I was hoping you could try the next one for us. We're going to go to part B, and they want the cosine inverse of -1. So we want to decide if -1 is an acceptable value. I know in the last one we did, we had some weird value and it didn't really work out because it wasn't part of the correct range. So before we even do any of the work, we want to decide if this solution even exists. So we want the arc cosine of -1. So what do you think? Does this one have an actual solution?
I think so.
I think so too. We know that if we graph cosine, it oscillates between +1 and -1. So it absolutely does have that in the solution set. So we're good to go ahead and continue now that we know it exists. So the tricky part about this is finding the reference triangle that has this measure of cosine. How do we want to set that up?
I don't know.
So let's take a look at the definition of the cosine function real quick. Cosine is x over r, which means the inverse cosine of x over r equals theta. And it looks like we don't have a fraction, we just have one number. So really we could say we have -1 over 1. We have arc cosine of -1 divided by 1. And the reason we want to write it like this is because we can clearly see that x has to be -1, and the hypotenuse of our reference triangle is going to be +1. So that limits us to quadrant 2 and quadrant 3 because the other two quadrants give us positive cosine values. So I'm probably just going to stick with quadrant 2 for this one. That's where our angle is going to be. So we have an x-coordinate of -1. But notice how the hypotenuse is also 1, which means that we don't have an ordinary triangle. We have a quadrantal angle here. We have an angle that coincides with the major axis. And that's just something I can tell right away by the fact that the absolute value of our x is the same as the r. Ordinarily, we know that our hypotenuse would be slightly larger than x. But as we go down and go down more and more, it actually coincides with that value. So what angle is that going to be, though? Imagine we start at our normal place. We start at 1, 0, and we go all the way around. What angle is that?
180.
Exactly. So our answer to this one is either 180 degrees or pi. So the answer to the question, what angle gives us a cosine value of -1? That angle is pi. So it looks like we are out of time for today. Stick around. I'm going to assign in a little bit of homework just to further conceptualize these ideas. Is it okay if I erase this?
Mm-hmm.
So we are on page 349. And I want you to do 1 through 16 odds only, and 19 through 34 odds only. And just a few more, maybe 37 through 42 odds only, and then we're done.
Okay.
All right, that's it for tonight. I'll see you tomorrow.
Okay, see you tomorrow.